In this lecture, I will be focusing on the basic principles of filters and filtering. Filter is a device which is used to remove some frequencies and pass some through it. There are four different types of filters. Low pass filter pass low frequency and attenuate high frequency. High pass filter pass high frequency and attenuate low frequency. Band pass filter pass a band of frequency through it and attenuate the rest of it. Band reject filter reject a band of frequency and pass all other through it. We have a kind of analysis which is known as a frequency response analysis or characteristics, which is basically a plot, a graph between the transfer function with reference to frequency as x-axis and transfer function impulse response in the y-axis. We have a transfer function which can be in various forms or domains. A transfer function hw is equal to v naught over I naught in w terms means that it is in the continuous frequency form, and in the S form is a kind of, you can say, a complex frequency form which is in the Laplace form as well, where S is equal to JW plus psi has to be included over here. It is a kind of mistake over here, and a transfer function can be in the form of HZ V naught Z over VIZ in the Z form. So which kind of transfer function expression is used for analog signal processing and for digital signal processing? Normally these two are used for the analog signal processing, while this one and the HK, which is the DFT form, and this is the Z form, are used for the DSP digital signal processing. Here are some graphs which are showing the response or the frequency analysis or the frequency characteristics of different ideal filters. This is an ideal low pass filter in which this is the pass band and this is the attenuation band. These frequencies pass through it and these attenuate through it. Here we have the y-axis is the impulse response of the filter and the x-axis is the frequency. This is for a high pass filter which attenuates the low frequencies and passes the high frequencies. This is a frequency characteristics and graph for a band pass filter which passes a band of frequency and attenuates the rest of it, while the band reject filter attenuates some frequencies and passes the rest from it. These are basically the ideal responses of the filters. A pass band is a kind of band which passes frequencies and attenuation band which attenuates the frequencies. Now we can see that we have a circuit diagram of a low pass first order RC filter, and we are to derive the transfer function of that filter or the impulse response of that filter. So the transfer function of that filter will be calculated with the help of output over input voltages, and we have these two passive elements over here and we need to calculate their impedances. If there is a resistance, then its impedances will be like this. If there is a capacitor or an inductor, then their impedances will be derived from these expressions. So by using these expressions and by applying the KVL in this loop, we are able to calculate the input voltage, and the output voltage can be calculated from here, and we can then calculate their ratio to calculate the transfer function of the filter and further simplification, and then we uh, can replace WC over here with CR, and 1 over WC will come over here. So WC is equal to 1 over CR will be the cutoff frequency of that filter, and under which the frequencies pass through that low pass filter, but greater than that frequency the frequencies attenuate through it. So this is the cutoff frequency, which is WC. And we can also say this plot in which we have y-axis the transfer function and the x-axis as the frequency, also a Bode's plot. And when we graphically draw this response over here, it will be like that, and after the WC it will be a kind of attenuation, and before the WC it will be a kind of pass band, and the attenuation for the first order filter will be happening at minus 20 dB per decade, means 10 values of the frequencies. And this is the calculation procedure, which is by putting different values of W, we able to arrive at these values of HW, and then we can plot that graph. So if we have higher order filters than the first order filter, then this kind of slope will be a kind of more steeper. For the second order filter it can be minus 40 dB. For the third order filter it can be minus 6 dB per decade. So higher the order of the filter, then the more ideal will be the response of the filter, and more steeper will be the attenuation band roll off. So we have for the first order filter we can do the rearrangement in the transfer function by replacing the W with S, and we can arrive to this expression of the transfer function of the first order low pass filter. So we also can conclude over here is that higher the order of the filter, more ideal its response will be, and more steeper will be the roll off, and it will approach towards the ideal conditions. Now we have another kind of filter, which is an RLC second order low pass filter. A filter can be uh, made with active as well as passive elements. With passive elements it can be made with the help of RC, RL or RLC circuit. RLC circuit is normally the best out of all. So here is an example of a kind of second order low pass filter which is made from RLC elements, and by calculating the impedances of these passive elements we apply KVL over here to calculate the input voltage and then the output voltage, and then calculating their ratio, transforming them into the S expression, and then further simplification to get the transfer function of the second order filter. And then we can also say that from this transfer function we analyze this kind of cutoff frequency, which is 1 over under root into LC, and when we plot that transfer function in the Bode's plot we can see that it is a kind of pass band till here and attenuation band start from here, and it is a second order low pass filter, so its roll off is more steeper, which is minus 40 dB per 10 values, which is more steeper than the first order filter. We have another example of a kind of filter which is a kind of second order RC low pass filter. We can say that we can also made the second order low pass filter with the help of RC element instead of RLC. For that we can do the cascading of the filter, just attaching the R and C component in parallel to increase its order till the number of filter is achieved. But it is the better is the RLC filter because it has less elements, and due to those less elements there will be less kind of attenuation, and no external amplifier or less external amplifier will be utilized to enhance the signal level. So this is a kind of RC filter second order low pass, and its mathematical, its transfer function is this one. Then we have, after the low pass filter, the high pass filter, which passes the higher frequencies and blocks the low frequencies. And here are two circuits of the first order high pass filter made from RC element, and the second order RLC filter made from RLC components. And for the first circuit we calculate the impedances, we apply the KVL to calculate the input voltage, we calculate the output voltage, and then we can calculate the expression of the transfer function of the high pass filter, which is this one, and its cutoff frequency will be 1 over CR. And for the second order high pass filter, we do the same exercise and calculates its transfer function as well, and we can plot their Bode's plot and we can do their comparison. It is a kind of graph which is opposite than the low pass filter, and here we can see the second order high pass filter is more towards the ideal filter characteristics than the first order high pass filter, which is rolling at minus 20 dB per decade, and it is rolling at minus 40 dB per decade. So higher the order of the filter, the more ideal will be its response. Then we have the band pass filter, which pass a certain band of frequency through it and attenuates the rest of it, and they are also being termed as tuned amplifiers. And we can also say that the combination of the characteristics of the low pass and the high pass filter can lead us to the characteristics of the band pass filter, which is like this, where we have two cutoff frequencies. One is the low cutoff frequency and other is the high cutoff frequency. So this is the characteristics of the band pass filter, and the band pass filter comes in various orders: first order, second order, and many order filters. And we can also see an example of a band pass filter over here. This band pass filter is basically constructed from low pass RLC second order filter, and in the low pass RLC second order filter we have rearranged the resistor, capacitor, inductor elements, and it becomes a kind of second order RLC band pass filter. So it is just involving those elements with the shuffling of those elements with their position changed. A band pass filter becomes a low pass filter or a high pass filter. And when we calculate its transfer function after KVL, input voltage calculation, output voltage, calculating the ratio, then it is like that. Then we have band reject filter, which reject a certain band of frequency and passes the rest through it. It comes is also in various orders, and it is also a combination of the low pass and band pass filters characteristics. When they are used in combination, they can be a kind of band reject filter. It is a kind of notch filter. We can say it V notch filter as well. And there are certain ways to construct those notch filters, which are T-twin filter, but they are beyond the scope of this book. So in the passive filter, there were some kind of problems due to which we have focused on to moving towards the active filter. The first one is the cascading problem, because higher the order of the filter, there will be more cascading of the RC, RL or RLC components in parallel with the filter, which results in the drastical decreasing or attenuation of power. So we need some external amplifiers to raise the signal level. So that is a problem, and also an impedance matching is a problem in the passive filters. In order for maximum power transfer, we have to have impedance matching. So if we have inductors present in our filters, they generate their own internal noise, which is also a problem. So due to these defects in the passive filter, we move towards the active filter, which are made from operational amplifiers. Now we can see how we can design the passive filters, and for the designing of the passive filters we just need its transfer function, and from that transfer function we just need its cutoff frequency. So cutoff frequency relation when it comes from the transfer function, and in this example we can see that we have to design a low pass filter for a cutoff frequency of 1 kilohertz, and we already know from the transfer function of the first order low pass filter that WC is equal to 1 over RC, and we are already given the cutoff frequency. So WC is equal to 2 pi f. 2 pi comes over here, and we have the cutoff frequency over here. We can assume any one out of these two components, passive components, and we can calculate the one which is missing, and we can construct our low pass filter, which is this first order low pass RC filter. Then in order to construct a second order low pass filter, we have to know its transfer function, and from that transfer function which we have analyzed previously, we see that WC is equal to 1 over under root LC. So WC is equal to 2 pi f, 2 pi come over here, and then we have the cutoff frequency which is being put over here. We have assumed the capacitor value, and we can calculate the inductor value, and then we can analyze that second order RLC filter. We can also design higher order passive filters by just attaching in parallel these filters of different combinations. If we want to construct a third order filter, then we can use the first order and the second order, and we can calculate both of their transfer function. We can do their multiplication with each other, and after multiplication we get the WC expression, and from that WC expression we can put the value of the cutoff frequency, and then we can assume some values, and we can calculate some other values. In this way we can design our any order passive filters. Now to design our active filters, we need to have the transfer function of that filter. For example, we have to now design an active filter of the first order low pass. In the expression of that low pass first order filter is WC by WC plus S. Here we can assume WC is equal to 1 for simplification, and we know that HS is equal to YS over XS by doing the cross multiplication, and by further simplifying and multiplication we get this kind of expression, and then by inverse Laplace transformation we get this kind of derivative equation, which needs to be simulated in terms of some kind of analog computer. This is the analog computer which is used to simulate that equation. Here you can see that we can move the dy by dt value towards left and all the rest values towards the right, and we can assume that over here we have dy by dt, and from here we want to go to yt, and we have a summing integrator which does the negative integration of dy by dt, which is minus yt, and then we can use the inverter over here to invert that value to yt, and we can replace our dy by dt by this expression that it is equal to minus yt plus xt, and we can replace over here the dy by dt by xt and then feedback it towards backwards. So this is a kind of derivative equation by which we have simulated this kind of analog computer, and here how we have designed an active filter from the derivative equation. So we have two kinds of networks. One is the feedback network which is recursive, and one is the non-feedback which is non-recursive, and we can see that we have different orders of the differential equations, and the highest power in the differential equation derivative is indicating the order of the filter. So second order differential equation will be leading towards the second order filter, and the first order differential equation will be leading towards the first order analog filter. And the derivative equations are simulated by the operational amplifiers, and operational amplifiers which are forming a kind of filter circuit or analog computers. So these kind of analog filter realizations are basically studied in order to get us motivated for the design of the digital filters. These are the motivations for the design of the digital filter. Now we have another example, and we have in that example over here we have the differential equation, and with this differential equation we need to simulate it with the help of analog computer. So what we do over here, we rearrange the highest value of the derivative towards the left hand side and all rest towards the right hand side, and we assume over here that we have over here this value of d cube y over dt cube, and from here we want to move towards yt, and the summing integrator will be doing the negative integration, and then again second one will be doing the negative integration, it comes to this value, and the third one will be doing the negative integration, and then the inverter will be leading towards the yt, and then we can replace dy cube y by dt cube with these values, and these values come as feedback with some multiplier with some inverter, and we can feedback these values, and we can also include the xt value and multiplier included over here, and we can replace the d cube y by dt cube with these kind of values as we can analyze it from the equation. So this is a kind of integration method by which we can able to simulate our differential equation into a analog computer. We have another method as well to simulate our differential equation, which is a kind of differentiator method, which we will be studying over here. This is another example. In this example, we need to apply the differentiator method. So for that method, we have to keep the y value on the left hand side and all other values on the right hand side, and we have x and y, and then we have the summer, we have the delay element, we have the multipliers, and with the help of these differentiators we can calculate the dy by dt, and this differentiator d cube d square y by dt square, and with this differentiator d cube y by dt cube, and these are the multipliers, and we can summate all these values and the input also after multiplier coming towards summator as well, and all these values are added to provide the simulation of this differential equation of an analog filter. So this is the study we have done, because this study was needed for the realization of the digital filters. In this analog filter active filter designs, we use differentiators as well as integrators, while in the construction of the digital filters we use the D flip-flops, which are indicated by the Z delay elements. Thank you very much.